In this video, we'll take a look at the definition of a sequence and then look at some of its properties, some different types of sequences, and then end with what we're really interested as far as what do we do with these sequences, right? But in order to get to that point, we have to have a good idea of what a sequence is. So a sequence is a function where it's a special type of function where so a function whose domain is the set of integers, usually non-negative, but I'll say a set of integers, and then in parentheses I'll put usually non-negative, right? And whose range, right? And whose range is a subset of the real numbers. So is a subset of real numbers. Right? So as far as the thing that distinguishes a sequence from functions that we've used before or prior to this is the fact that the domain is only integers. So these sequences that we're going to look at are only defined for values that correspond to integers. So you'll never get a sequence like plugging in 1/2 into a sequence or pi into a sequence. The only numbers you can plug into a sequence, right? The ones that are in its domain are integers and usually non-negative, right? So to give you a sense of what they are, I want to kind of do a comparison between the functions that we've used up to this point, especially the ones that pretty much dominate what we do in the first semester of calculus, and then versus the sequence. So let me just kind of do, let's say, functions versus sequences. First with the notation, right? So we typically denote a function. If we're using our standard variables, we usually denote them like y equals f of x, assuming the function is explicit, right? So if the relationship is explicitly defined, we usually denote it like this. And then as an example, you might have y equals, let's say, 1 plus 1 over x, something like this. For sequences, we typically use like a and n, or b and n, or c and n. So we typically use n as our independent variable, and we normally use like a, b, and c for the dependent variable. So you might see something like this, like a sub n equals a function of n. So something like that, right? So you can use this f of n very similar to the way we use our f of x, but alternatively, you'll actually see it written like this, where this is the name of the function, and then this is its variable. This is the independent variable, this is the dependent variable, and this is what it tends to look like in the explicit form. Right? So for instance, if I wanted to make this a sequence, I might write it as something like a sub n is equal to 1 plus 1 over n. Right? Now, what really so you look at this and you're saying, okay, we're just playing around with letters, right? We haven't really made any fundamental change. Well, the big change is, for instance, if you try to visualize these, so if you graph this function, so obviously it's going to have a vertical asymptote at x equals 0. and then as x gets bigger, this term approaches 0, so the function approaches 1. So it actually has a horizontal asymptote at y equals 1. So, it basically, this is the line y equals 1. And if we were to sketch this, so if we sketch this like we normally sketch a function of a real variable, meaning all real numbers that are in the domain, then it would look something like this. Right? So this would be the graph of y equals 1 plus 1 over x. If I now set to sketch this sequence, because I am limited to only integer values in the domain, instead of seeing a nice curve like this, what you will see, right, it will still be asymptotic to the horizontal line y equals 1, but instead of seeing a nice curve that's going down like this, you're going to see isolated dots like that. And these would correspond to the integers. So for instance, this would be 1, this would be 2, this would be 3, and 4, and so on, right? So it's like when you go from a function to a sequence, right? So you go from a function of real numbers versus function of integers. It's like you remove, big segments of this graph, and what you're left with is just literally a sequence of isolated dots, right? And again, there are two words we can use to describe the big difference here. So on this side, this function, right, represents something, a process that is continuous. Right? So for instance, there are no breaks or holes or gaps in this, right? And again, we're familiar with the word continuous, or the concept of continuity, right? Well, on this side, we have a whole bunch of gaps, right? All we have are these isolated dots, and this is what we refer to as a discrete process, right? So continuous versus discrete. Function of a real variable, function of a integer variable, right? So a nice little comparison there. And let's just continue with some other differences, right? So if we look at, so going back to this, my example here of a sub n is equal to 1 plus 1 over n. When I write this, again, there is no real restriction on n. Like it doesn't really tell me that, okay, I can only use integer values. So what we would like to do is add some more to this to make it very clear, right? So that someone just looking at it would know that this is a sequence, right? This is a sequence, which means I can only evaluate this using integer values. Well, what we tend to do is this. We might take our symbol a sub n, and we might wrap it in braces, and then as a subscript here, we might put a little n, and then have it start at, let's say I want the sequence to start at n equals 1. Then I would put a 1 there, and then to indicate that it continues indefinitely after that, I put infinity there, right? So then it's a little clearer now. You could say that, okay, here are the terms in my sequence, right? So we refer to these as in fact, let me write this down. Refer to this as our general term, right? And then here's our general term, but we could say this: the terms start when n equals 1, and then it goes on indefinitely, right? So, and the n here is, again, you can refer to it as your variable. A lot of times it's also referred to an index, right? So you can refer to something like this as your n as an index, and we will use n as our main index slash variable for a sequence, but you can also use things like k and j. We tend not to use x and y because, again, we want to make a distinction between what we use to represent a function of real variables versus a function of integer variables, right? And then so this number here is often referred to as the initial value, right? So the initial value or the starting value of our sequence. So initial or starting value. Oh, let me clean this up a bit. So initial or starting value, right? And once you do that, then now you almost have a sense of, okay, what is the first term in the sequence? What is the second term in the sequence? What is the third term in the sequence? And so forth, right? So, for instance, now let me add a bit more detail to this. So sometimes I could do this. You might see the actual general term in braces like this. And then, now notice for this one, because I have this 1 over n, I could not start it at n equals 0, right? Because 1 over 0 isn't defined. So we want our sequence to be defined on whatever set of integers we indicate. So in this case, let's say I started at n equals 1, and then it will always go to infinity because, again, it's a function of all the integers, but we have to define, or a particular question will define what integer to start with. So I could also make a list of these values to say, so for instance, when n is equal to 1, I have 1 plus 1 over 1. Oh, come on, 1 over 1. When n is equal to 2, which would be the next integer, you see, you skip all the numbers between 1 and 2, and then you go straight to the next integer. When n is equal to 2, we have 1 plus 1 half, and then when n is equal to 3, we would have 1 plus 1 third. I'll write one more term, 1 plus 1 fourth, and then to indicate, and this is important, to indicate that this goes on forever, we use our ellipsis, right? Just means and so on, and then we can close it. So you can have a notation like this, which indicates the general pattern in the sequence, where it starts, and it's never ending; it's always infinite. Or you could have a description where the first 3 or 4 terms are listed, and then it says and so on, right? So actually, it typically wouldn't be listed like this. These sums, right? These additions would be computed and simplified, so we would end up with 2, and then here we would have 3 halves, and then here we would have 4 thirds, and then here we would have 5 fourths, and so on, right? And because of the order in the set of integers that we're using, there's always a well-defined first term, right? So the 2 here is often referred to literally as the first term in our sequence. Right? And in this case, again, if with this as my a, I can indicate it as a sub 1, right? Because the integer 1 is the first value of my index. So when I evaluate my sequence at that initial value of my index, I will get the first term. And then this would be my second term. And it would be indicated a sub 2. This would be my third term, and then this would be a sub 3, and so on, right? So there's a sense of order in the fact that these function values are listable. You can list them. You can't list the function values on a continuous function. Just looking at this, like, where does it start? Like, where does it start? Because technically the domain would be everything except 0. So, like, what is the next number after 0? Well, there is no next real number after 0, but there certainly is the next integer after 0, and that would be 1. So the function values on a continuous function like this are not listable. You can't list them, but clearly these are listable. You can say that's the first function value. So like on the graph, this would be a sub 1. Or actually, let me make it even clearer. Let's go back here. So this would be a sub 1. This would be a sub 2. This would be a sub 3. This would be a sub 4, and so on. Right? So these would be the function values that correspond to the integers. All right. So let's do another example of this, just a simple one. So here's an example of another sequence. I will use, let's say I use B this time. So the sequence B, and in this case, let's say we start it at n equals 0, and again, always goes to infinity. And let's say it's of this form, like 1 over 3n minus 2. Right? That's our sequence. Let's say that the first, the first 3 terms, right? So in this case, the first term would correspond to n equals 0. So my first term would be a sub 0, and then it's just a matter of plugging it in, right? So actually getting the values of the sequence in an explicit sequence like this is fairly simple. You're simply just plugging in whatever number corresponds to that particular term. So the first term here would be a sub 0, and that would be 1 over 3 times 0 minus 2, so that's negative 1/2. The second term in this sequence would be a sub 1, right? Not the 2, because we're actually starting our index at 0. And it's kind of a big thing in computer science or math, where do we start our index? Do we start our indices at 0 or at 1? It doesn't really matter, actually. You can always re-index it to start wherever you want and get the same sequence, right? So it's really irrelevant where you started. But in this case, plugging 1 in will give us 3 times 1 minus 2, so that's 1. And let's just do a couple other terms. So the third term in this sequence would be a sub 2, and that would correspond to 1 over 3 times 2 minus 2, so that's 1 over 6 minus 2, so that's 1/4, right? And so on. I'll just say, so in general, the nth term, let's see if we could write down the nth term, and this is where you'd have to be careful. Look at the pattern. The first term, you'd plug in 0. The second term, you'd plug in 1. The third term, you'd plug in 2. So the nth term, you'd have to actually plug in a sub n minus 1, right? So it's, again, because we're starting at 0, it's like our counter is a little bit off. To get the first one, we plug in 0. To get the second one, we plug in 1. So the nth term in this sequence is actually 1 over 3 times the quantity n minus 1 minus 2. And then if you wanted to simplify this, you would end up with 3n, and then you distribute the 3, so you'd have a minus 3, and then you subtract the 2, so you'd end up with minus 5, right? So just again, it's just showing some of the little calculations that are involved in this, right? Now, so this is an example of an explicit sequence, but you have other sequences where you can't just get the terms by plugging in the value of your index. Like, so I could, like in this case, because this is a function of my index, I can just evaluate it by plugging in whatever integer I want. So if I wanted the 20th term, all I would have to do is plug in 19 into this, right? And I would get it, right? But sequences can also be defined what we call either implicitly or recursively, right? So an implicit or recursive sequence is one in which successive terms, right? So successive terms are functions, or let's say it this way, are dependent on previous terms, right? So in other words, instead of having just an expression in terms of the index that you can just evaluate, in an implicit or recursive sequence, you might have to know the previous terms before you can figure out the next term, right? The successive terms. So what do they look like? Well, let me give you a simple one. So a sub n might be equal to a sub n minus 1 plus 2, something like this, right? So this is saying the next term in the sequence is equal to the previous term, because if you notice, this is like, if n is an integer, then n minus 1 would be the previous integer. So this term would be before this one. So this is my successive term, this is my previous term, and this rule is telling me to get the next term in the sequence, I take the previous term and I add 2 to it, right? So this kind of gives us the relationship between terms, right? So this is the relationship between the terms in the sequence. But it doesn't tell me where to start. You see, it doesn't tell me, okay, well, where do I start? And with what value do I start? So in a recursive sequence, not only do you need to have the relationship between the terms, but you also have to have what's called like an initial condition or a seed value or something of the sort. So in addition to giving this general relationship, I would have to say something like a sub 1 is equal to, let's say, 2, right? And this now is what we call the initial condition or the initial value. So initial value. This tells me where it starts. So here my initial value of this sequence is 1, and then I can use this along with this information to generate the rest, or at least the next few terms. All right, so let's see if we could do that. So now so in this case, again, we're going to list, let's say we list the first 4 terms. Well, the first one is already given. This is considered a term. So a sub 1 is equal to 2. This is my first term in this sequence. To get the next term, which I know would have to be a sub 2 because I'm only working with integers, that's where I use this relationship. So a sub 2 would be equal to a sub 1, right, the previous value of my index, so it'll be a sub 1, and then I add 2. But I know what my previous value is, it's 2. So I plug it in. So in other words, I have to know this in order to figure this out. So then I do 2 plus 2. So this is the next term, right? This is the second term in my sequence. If I wanted to find the third term, well, I use that same relationship. Again, the relationship says if I want to find a sub 3, I would have to take a sub 2 and add 2 to it. So a sub 2, right, plus 2. So there, again, I am taking the previous value in my sequence, adding 2 to it to get the next one. So in this case, it's 4 plus 2. That gives me 6. You notice what we're generating? We're generating the even integers, right? Positive even integers. So this is a recursive way that you can generate it. You can do it explicitly as well, but this is a nice recursive way. And then, like I said, let's do our fourth term. So the fourth term would be a sub 4. And then again, based on the rule, to find a sub 4, I would have to take a sub 3 and add 2 to it. So a sub 3 plus 2. I know what a sub 3 is. That is equal to 6. Plug that there. And then evaluate. 6 plus 2 is 8, right? And so on. So the idea of these recursive sequences is that you can't, so for instance, in general, right, you can't just jump to like the 1000th term. In principle, you would have to evaluate the previous 999 values and take that information to generate the 1000th one. And the reason I say that is here, this particular example just requires you to know the direct predecessor, right, of this term. So you'd have to know just the one right before it to figure out the one that comes after. But you do have some relationships where you have to keep more information than just the very last one. Here's another example of a recursive sequence, right? So let's use B this time. So you might have B sub n is equal to 2 times B sub n minus 1 minus 3 times B sub n minus 2 plus B sub n minus 3. So now you have to know the previous 3 terms in order to generate the next term. So for me to kind of give you an initial to start the sequence, I would have to give you 3, right? I'd have to give you 3 initial values. And let's say we start it at 1 again. So let's say B sub 1 is 1. B sub 2 is negative 2, and then B sub 3 is equal to 4, right? So I'd have to give you all of this information along with this general rule in order for us now to start generating the rest of the sequence, right? So since I know the first 3, let me go ahead and write those down. So B sub 1, B sub 2, B sub 3. So these values are given. These are all our initial values. So the next one now that isn't given would be B sub 4, right? The next integer. So let's write down what the rule says in general and then plug in the values. So this is saying take 2 times B sub 3 minus 3 times B sub 2 plus B sub 1, and that will give me B sub 4, right? So take 2 times 4 and then subtract 3 times -2, and then add 1. So plus 1. And let's do our arithmetic. So we got 8 plus 6 plus 1 for 15. So this is now the fourth term in our sequence, right? So the first 3 were already given. Those were our initial conditions. But to get the rest of them now, I have to use my general relationship. So let's say I want it. Let's do this a couple more times so we can see the pattern. So b sub 5, that will be 2 times b sub 4 minus 3 times b sub 3 plus b sub 2. So again, we have all this information. It's just a matter of keeping track of it and then using it as needed. So it's 2 times b sub 4, so that's 15, minus 3 times b sub 3, which is 4, plus b sub 2, which is -2. And then let's evaluate this. So we'll have 30 minus 12 minus 2, right? So that's 16, right? So here are the first 5 terms in this sequence. 1, -2, 4, 15, 16. You look at it, it doesn't really seem like much of a pattern, right? But the pattern is given right here, right? It's given right here. So it's not something that, you could probably just look at and tell what the pattern is, unlike our previous example where we were just generating the positive even integers, right? Here it's a little bit different, but we're following the same process. Right? Let's do one more sequence evaluation here. So b sub 6. So we would take 2 times b sub 5 minus 3 times b sub 4 plus b sub 3. So again, use the values that we already have to generate the next one. So we'll have 2 times b sub 5 is 16, and then minus 3 times b sub 4, which is 15, and then plus b sub 3, which is 4. So plus 4. So what do we have here? We have 32 minus 45 plus 4. So 32 minus 45, that's negative 13, plus 4, that's negative 9. Not what I would have guessed, right? And you probably didn't guess this either, but this is our next term, right? So that's just kind of a brief introduction to sequences, what they are, what they look like, some of the notation, and the different kinds of sequences. In the next video, we're going to focus on the big thing, right? The big concept that we want to be able to apply to this new type of function. So if you want to see it, just hop on over now, and we'll explore together. See you then.